on the one hand, Niels Bohr described the electron as a canonical point mass orbiting about the proton in the hydrogen atom by using Newton's second law, Coulomb's law, and in order to derive his formula for the total energy, the velocity, and the momentum. Okay, but on the other hand, which is more important, I think, is to try to incorporate de Broglie's idea of matter wave into his atomical models by assuming, to be specific here, assuming electron behaves like the wave. And in this case, it's not a plane wave, but a standing wave. Standing wave confined by circumference, because after all, he still trying to visualize the motion of electron as a circular motion. So therefore, he argued about those orbit which can accommodate multiple of the de Broglie's wavelengths are stable. Okay, so that is the idea from standing wave for the stationary orbit in atom. Okay, so standing wave in a wave when you start in physics, and then the stationary orbitals in Bohr's hydrogen atom theory. Okay, let's continue. So by assuming the electron behaves on the one hand as a particle, circular, moving around the proton, and also have to take into account of the wave behaviors of electron according to de Broglie's formula. Bohr derived the condition is called the quantum condition. So this is called the quantum condition. The quantum condition. Of course, this quantum condition can be written as a different form. For example, what is the product of the P? It is angular momentum. See, so that is L equal to R multiplied P. That is angular momentum. Okay, so Bohr's therefore the Bohr's quantum condition can be simply written as L equal to and N multiply H bar. So what is H bar? H bar is equal to H divided by 2 pi. So all of these forms, when you see in the textbook, are called quantum condition. It's called a quantum condition. We'll start from the quantum condition here. It's very important, although it's empirical. It's called the quantum condition. By applying Bohr's quantum condition, and the total energy can be solved. Of course, in Bohr's theory, there's many emphasis on the orbit, because that's why when we're looking backward in perspective, so the Bohr's ideas is based on the visible model, in which you can actually see the electron orbit the center, the nucleus, the proton in this case. Okay. On the one hand, he wants to keep that idea, so-called orbit, or like his orbit of the Earth. This is purely analog of the solar system. Okay. But on the other hand, he also knows that there are some limitations, because as we explained last time, if we just consider the electron is actually a change with acceleration, the charged particle with acceleration, inevitably they will emit the electromagnetic wave, right, or radiation. So by introducing standing waves, Bohr argues that under these quantum conditions, okay, the electron will not emit. So electron, although they got acceleration, so the electron, actually the hydrogen electron, so no radiation, no electromagnetic radiation. So radiation. no radiation occur. Okay, inside atom. So that is what we call the stationary orbit. So this orbital, Bohr's orbital is not any orbital, but those orbital who satisfied his artificial, man-made condition, or so-called quantum condition. So this orbital is one of these called a stationary. Stationary is orbit, stationary state, or called a stationary state, okay, in which no emission. So no emission. You're trying to say, well, if the electron move is located in this so-called stationary states, no emission. Of course, it's just hypothesis. Okay, there's no theoretical explanation in his days or by himself. Let's just continue this derivation. What can we do next? In this case, can we just provide some space here? Okay. Just trying to finish this derivation on the single page so that we know it's a stationary, so it's stationary, and yet there's no better alternative in Niels Bohr's time. Okay? There's no better alternative. So let's to cut the story short, let's focus on some of the highlights toward the climax in his derivation, how Niels Bohr first derived his analytical formula, although it's by nature it's empirical. So let's just put this into this box here. So let's just do some. Okay. So let's just combine this formula together. It's not far away. See, from here you can see the 2 pi. Can we start from any of them? Can we start from this this condition? From this form, from this quantum condition, we see that R multiplied the P were equal to N multiply H bar. Okay, just pick up one of the quantum from one form. I prefer this form because there's not much decoration. It's just right at the essence of this quantum condition. So from here you can see R and P, the product of R and P, which is actually the angular momentum, equal to a product of N multiply the H bar. N equal to 1, 2, 3 is integer. So this implies that the product of R and P, or angular momentum, must be discrete. Okay, so this is something new, and we know that the any velocity and momentum, angular momentum, are continuous in Newton's mechanics, right? But not in this case. If we introduce the de Broglie's matter wave, or we are obliged to describe the electron as a matter wave. In particular, in this case, the standing wave, the standing matter waves inside the hydrogen atom. Okay, let's just look for the formula. How do we find the product of R multiplied P? So we have found the formula here. The product R multiplied P, and where can we find multiply P? So this is R. And we have to work out the, okay, let's see. R, can we just write R here? Can we rewrite the P? Can we use the formula for the P? We put the P here, so that put the E in front of R, and that would be the formula for the P. That would be the M, can you see? MK divided by R. That is on the left-hand side. So these two R are identical, right? These two R are identical. So if you bring this R into this square root, so the left-hand side became E multiply the square root, MK R. You see that? That's the left-hand side, right? So if we just rearrange that one, so therefore, that will give us the idea how to rearrange this formula by putting the mkr equal to n h bar divided by E, okay, and a square, so that we can remove the square root. Aha, you can see in this formula, all other constant except the R. Okay, so we can in this case, we can find the formula for the R. The R represents the radius of one of the stationary orbit. So in this way, we can work out that. Can we put everything divided here? So we can put the k. We can put m k e. That is h bar square and n square. Aha, that is the first important formula Bohr did. So this implies that the radius of this orbit, so this radius, one of them, Rn, is discrete, okay, which is consistent with his idea that not all orbitals are stable except those so-called stationary orbit. So in this way, that is the first formula Bohr derived. I think he was very happy about that. That is R, n, we put n here, were equal to A1 and multiplied n squared. So what is N1? A1 is called the Bohr model. It's called the Bohr radius, which is the smallest radius, or distance, the electron between the electron and the proton, or the smallest radius. So that will equal to this constant. We can put all the constants here. Can you see? So A1 will represent all these constants. So h bar square, h bar square. Did we mention anything? No. We got mke, mke. Of course, you can go further by just rewrite this Coulomb constant k as 1 over 4 pi epsilon nu. Okay. If you combine this formula, you can get the expression which would be exactly the same as the one in your textbook. But this is intermediate, okay? This is not the final, this is not the climax. Remember, the objective of Bohr's theory is trying to explain that the energy formula, the total energy of electron inside the hydrogen atom, can be written as this form, okay? RCT are constant, and N is a variable. It's called discrete formula for the energy inside the atom, hydrogen atom. So next, we need to find the formula for the energy. Okay, the formula is here. The formula is derived by Newton's law and plus the Coulomb's law. So this is the formula Bohr first used to obtain his famous formula. That is the total energy. Because we know there's R here, we know the R here. What we can do if we just write the energy for the hydrogen atom En, which is negative, by the way, which is negative. So we got the Ke squared divided by 2R. We just multiply the formula. Can we just go to 2 A1 multiply N squared. Okay. And in addition, we can rewrite this form by introduce another formula, that is E1 as negative E1 divided by N squared. So what is E1? E1 is energy of ground state, the energy of the ground state, the energy of the ground state, the lowest energy, ground state energy, the lowest energy. Aha, you can see that this is aha moment. So finally, Niels Bohr obtained the formula for energy, which has exactly the form. You have the exact form compared with the empirical formula derived by combination, by combining the Rydberg's formula, Rydberg equation, and Max Planck's equation. Okay, so this is the key result Niels Bohr have derived. So if we just put this in together, that's one more page to explain. To summarize what we have obtained, on the one hand, empirically, we have derived this formula that is perhaps we start from the Rydberg's formula, right? The 1 over lambda is equal to R multiply m square, n square minus m square, m square, okay? And from here, we can see that when we multiply the Planck's, when we apply Planck's formula for photon, we got this hc divided by lambda equal to rhc, and n square minus m square. Okay, and to go further, we have rewritten this as the difference between the two terms. One is negative rhc divided by m square, take away of negative rhc divided by n square. So that implies that we have assumed that the energy of the total energy of the hydrogen atom, which of course is just the total energy of the bounded electron, is that E can be written as negative, a constant, rhc divided by the integer square. This is called the inverse square law, you see. Now, Bohr's contribution is that he actually obtained the two formula. One is a formula for the radius of those stationary states or circles, circular orbit. That is A1 multiplied n squared, where n equal to 1, 2, 3, 4. And more importantly, he actually found the formula for the total energy. This time is based on two steps. One is using Newton's law and Coulomb's law, and step 2 is to incorporate de Broglie's matter wave. And by treating electron in those stationary orbit as a state of the standing wave, okay, standing wave. So standing waves to the stationary states, okay. So that is Bohr's contribution. For each stationary state, the energy can be written as simply as a constant, the ground state energy divided by the n square, okay. And if you look at your textbook, this E is exactly equal to, the E is ground state is equal to 13.6. If you use the EV, electron voltage, as the unit for the energy. So that is a summary of the Niels Bohr's theory. Okay. So basically, he came all the way from the Rydberg's equation, and eventually obtained these two important formula. Okay. Perhaps we can also discuss a little bit the implication of the Bohr's model. Okay. For example, if we actually, the Bohr's model, the first formula, eventually we have to eventually abandon this formula. namely the orbital idea. You see, although Bohr mentioned Bohr has had considered the de Broglie's wave, but he still, uses the particle model to describe the orbit of electron. So in many textbooks, you will find that they use this co-centered circle to describe the Bohr model. So what is, so basically that's what you can see, that in Bohr model, you will see this is diagram, in the diagram here. So we can see the Bohr model, we just as a different circle. You can see that's circle 1. This is orbital 2, orbital 3. And of course, this looks nice, okay, just like a target. And then you can, in chemistry, what people do is just simply put the electron, okay? They call it a shell, okay? Actually, they are very clever. They don't call it the orbit anymore. They call it a shell. The shell is, they're trying to avoid or distance from this idea of orbit. So it's called a shell. They call it a shell. And they just put the number of different electron. This called this, by doing so, they are doing the configuration. So you are doing the electron configuration. So that's how in any textbook, that is how people to make the atom based on Bohr's model. But bear in mind, this diagram are wrong. Okay, why? Because when you draw this diagram, they didn't follow the scale of this n square. Okay, because it's quadratic equation, isn't it? So basically, if you want to draw this, if you make it more reliable diagram here, so what I can see is that if I use this quadratic relation, can you just put a quadratic relation here? Oops. We just draw a few of them because the quadratic equation increase very fast, you see. So if you just draw a quadratic equation to describe the radius of each stationary circle or circular orbit, that is Rn. So this is Rn. This is n. Is n. So how many orbitals can we write here? We got there's 1 and 2 and 3 and 4. Oh, we better stop here. So, okay, because we have, if you want to draw the first, if this is 1, so this is 1, so this is this Bohr orbit. This is Bohr. So A1 is called the Bohr radius. Bohr's radius, the smallest smallest radius in hydrogen atom, or smallest distance between proton and electron radius. Okay, so you can, this is 1 here, but when you got a 2, they become 4. So 1, 2, 3, 4. That would be 4. That would be 4 radius, Bohr radius. Okay, that become, the radius will jump to 4. And if you come to 3, well, that's beyond this scale. You can see this is 5, 6, 7, 8, 9. It will be here. It will be here. So you can see the quadratic dependence of the n square of the n must be taken into account if you want to draw a realistic Bohr model. See, Bohr model like this. So that is the orbit of each circle or stationary. So that would be, can you see that is 1, that's 2, 3 would be somewhere here. So how to draw the Bohr model using the exact scale? So then you can say, well, it's very hard. I can see that. I can tell you it's very hard. So this is the center of atom. This is the center of this is where the nucleus located. So if I draw the first circle, I making a smaller circle. So this is the first circle. Make it smaller so that we can draw more, hopefully. And the second circle, the radius will be 4 times of this one. So the second circle will be 4 times of that one. Is that very close to 4 or probably too large? 1, 1, 2, 3. Yeah, that is second. Can you see that to be second? How about the third? How about n equal to 3? Would be 9. See, it would be 9. It would be like this. Ooh. Okay, I can hardly draw it. I can hardly draw it. Okay. Okay. Okay, I will stop here. I will stop here. So, because this is 1, this is 4, this is 9, probably even larger, right? Even larger. Okay. Makes it just make it larger. Now the reason I mentioned that the real scale is that the radius is actually is a bad idea. Okay, when you actually incorporate the wave behaviors of the particles. So this is, can write it down here. This is the first shell, first orbital is n equal to 2, is n equal to 3. Okay, this is n equal to 1. There's n equal to 2 and n equal to 3, which you can find in many chemistry textbook, right? Which is incorrect, okay? But of course, it is still it's a useful way for people to put the electron, to find the electron configuration by using this distort Bohr model, okay? When you talk about the Bohr model, you must actually draw the radius according to the formula for radius. Okay, so in history, I can talk about the issue again when we discuss the in depth about Dirac's idea of his idea in essence. Why should we? The reason why should abandon the orbital idea completely. Of course, this is not original idea. His original idea is come from the Heisenberg. Okay, Heisenberg. So this is a little bit discussing about the Bohr's formula for the radius of the atoms. Okay, so don't think that the Bohr's models are that great. Okay, on the one hand, he got the energy formula is correct, but on the other hand, the formula for the radius is actually meaningless. Okay, it's meaningless. So I will stop here, but in the next video, I will talk about the graphical implication of the or representation of the total energy of the hydrogen atom. By the way, it is also which actually exactly the same as the result you can derive by using Schrödinger's equations. I will stop here.